Dr.M.G.R. Educational and Research Institute, University, Madurai, Chennai.
Good afternoon to one and all present here. There is no end to education. The whole of life is a process of learning. I hope those who have joined here have chosen the path of learning. I am Dr. R. Nitya, working as Assistant Professor in the Department of Chemistry at Dr.M.G.R. Education and Research Institute, Madurai. It gives me immense pleasure in meeting you all for today's program, My Journey Towards Atomically Precise Nanoclusters by Dr. Prabhu Pandurangan, Assistant Professor at University of Madras. In the studio, we have our Deputy Dean, Dr. A.R. Arunachalam, and my dear colleagues, Mrs. M. Shashikala, Dr. D. Kavita, Mrs. M. Jeevaratnam, and Mr. Ganesh Babu, System Administrator. And now, let's start this program by welcome address. I invite Mrs. M. Shashikala, Assistant Professor in the Department of Chemistry, to give welcome address.
Good afternoon to one and all connected here. I, Mrs. M. Sasikala, Assistant Professor in the Department of Chemistry, I express my heartfelt gratitude to our beloved founder, Chancellor, A.C. Shanmugam Sir, and our Honorable President Engineer A.C.S. Arun Kumar Sir for encouraging and motivating us to conduct many number of online programs. I am also indebted to welcome our Vice Chancellor, Dr. S. Geeta Lakshmi, our respected Registrar, Provost, and other higher officials of our university. I'm very much happy to welcome our Joint Registrar, Dr. S. Ramalingam, Dean Dr. S. Manivannan, who has stands behind us in organizing fruitful events. I also take this opportunity to welcome our Deputy Dean Academic, Dr. A.R. Arunachalam, and the Deputy Dean Administration, Professor K. Sendil Kumar, who are always on their heels and keen enough to support and encourage the staffs for conducting valuable program. I feel immensely happy in welcome our today's chief guest, Dr. Prabhu Pandurangan Sir, Assistant Professor Senior Grade in the Department of Physical Chemistry, University of Madras. Welcome you, sir, to deliver a talk on the today's topic. I'm also welcome my department staff and Mr. Ganesh Babu Sir, who always render his helping hands in times of need to make this event a successful one. I welcome my dear students who are utilizing this opportunity for their success. Thank you all. Once again, welcome you all for this event.
Thank you, ma'am, for your welcome address. Now I request Dr. A.R. Arunachalam, Deputy Dean, Academic, to felicitate the gathering.
So thank you, ma'am. So very good afternoon to one and all connected here. So on behalf of Dr. M.G.R. Educational Research Institute, Adayalampattu Phase II campus, I would like to welcome you all to this national level webinar on my journey towards atomically precise nanoclusters. So to start with, I would like to thank our Honorable President Engineer A.C. Arun Kumar Sir for giving us approval to conduct this today's national level webinar. And I really thank him for his enormous support towards conducting a lot of online activities on various kinds of topics on recent trends, I could say. So I would like to congratulate the Department of Chemistry for taking the initiative to conduct this today's event on a very interesting or maybe very important topic, I could say. So I would like to congratulate the Department of Chemistry HOD, Dr. S. Vallimi ma'am, and then the other faculty coordinators who have involved themselves in conducting this national webinar, especially Dr. Nitya, Mrs. Sasikala, Dr. D. Kavita, Mrs. Jiva Ratinam, and Dr. Ramapriya, and as well as the technical support which is given by Mr. Ganesh Babu. So I really appreciate and congratulate the entire department for coordinating and involving themselves in conducting this national level webinar successfully. And then on behalf of our university, I would like to thank and welcome the speaker of today's session, Dr. Prabhu Pandurangan, who is part of School of Chemical Science, University of Madras, Ginty campus. So please welcome, sir. Thank you so much for accepting our invitation, for spending a valuable time with us on taking a very important topic in that particular chemistry department. So thank you so much. And I also thank all the participants for taking your time for registering for such kind of webinars where you gain a lot of knowledge. So our university has been putting a lot of efforts, taking a lot of initiatives in conducting a lot of online activities successfully on various recent emerging topics. And today is one more event conducted by the Department of Chemistry from our university, choosing the right topic, and I could say choosing the right resource person also. So on behalf of the university, I once again welcome all the participants as well as the speaker for today's session. So definitely, I think that this session is going to add more value on a knowledge transfer basis. So I also thank the department for giving me an opportunity to talk a few words. So I wish the department all the best, and wish this program a grand success. All the best. Thank you all.
Thank you very much for your wishes, sir, and thanks for joining today. And now I invite Mrs. M.G.R, Assistant Professor in the Department of Chemistry, to introduce our chief guest.
So, good afternoon to everyone. On behalf of Chemistry Department of Dr.M.G.R Educational and Research Institute, myself, M.G. Assistant Professor, delighted to introduce our chief guest for our today's program, Dr. P. Prabhu, Assistant Professor, Senior Grade, Department of Physical Chemistry, School of Chemical Science, University of Madras. He has completed postdoc in nanomaterials, Yonsei University at South Korea, and he has completed PhD in analytical chemistry at Madras University. He has more than 20 publications in reputed journal, and he has attended many national and international conferences. He is guiding research scholars. He is an invited speaker at many institutions that includes a professor program for faculty, and he has completed 2 research projects funded by DST and committed to 3 ongoing projects funded by RI and QI RUSA 2 for the total worth of rupees 1 crore. He has organized many workshops, entrepreneurship awareness program, FTP, skill development online trainings and seminars. We are fortunate to have you here today as our chief guest and deliver a valuable talk. Once again, I take this opportunity to welcome our chief guest, Dr. Prabhu. Welcome, sir. Thank you.
Thank you very much for the introduction, madam. And there is an important announcement to the participants. You can post your queries in the chat box, which will be answered at the end of the session. And you can avail your e-certificates by filling the feedback form, uh, which will be provided in the chat box. And I now invite our chief guest to deliver his valuable talk.
Thank you. Can you see my slides? Is my slide visible?
No, sir.
Hello. Is my slide visible now?
Yes, sir. Yes, sir.
Can I start?
Yes, sir. You can start. You go for a full presentation mode, sir.
Yeah, I think it is. Is now fine?
No, sir. It's not viewable. It's not. It's not in the PPT view only.
No?
No, sir, not you.
Is it now visible?
Yes, sir. Now we can go.
Yeah. First of all, before I start my lecture on my journey towards atomically precise nanocluster, I would like to thank the management of Dr.M.G.R University, and in special, I would like to thank the Deputy Dean of this university for inviting me. And also, I would like to thank the HOD of the Department of Chemistry, Dr. William Mike, and other faculties like Dr. Sasikala, Dr. Rampriya, and so on. Many of the faculty members are my alumni, either in Lyra College or University of Madras. I'm happy and delighted to present my journey towards atomically precise nanocluster. Since the audience is covering from UG to research scholars and faculty, few of my slides can be basic, some slides can be advanced. So I hope this journey will be as fruitful after lunch. Okay, so some may ask, what is this journey special about Dr. T. Prabhu? It's my research journey. Many of us had many time pass journey, but I think my journey towards South Korea, Yonsei University, has changed my research career. That's why I wanted to present the title as my journey. So after my schooling at Avadi, I have graduated from UG, Layala, and then I just wanted to point this map because at PG level we were able to work on bimetallic nanoparticle covering of gold and silver, which was ranging about 5 to 10 nanometer. I will be mentioning about the nano size particle because it carries importance with regard to my title. So you would have seen many papers on gold, silver bimetallic nanoparticles where gold forms the core and the silver shell, or the vice versa. Anyway, depending upon the synthesis strategy, one can tune the nanoparticle. And in the case of PhD, I was able to work on gold particle modified electrodes for sensors, where we could achieve 20 to 40 nanometer. And after my PhD, I was able to work at Yonsei University, Department of Chemistry, under the guideship of Professor Dongli, who happens to work in atomically precise cluster. I will go back to what is this atomically precise cluster in my following slides. You can see the size of this gold particle, which is 1.1 nanometer, highly monodispersed particle for sensor application. And coming back to University of Madras as a faculty, and you can see there is a time reversal plot where we learned in the thermodynamics about time reversal. Time reversal cannot reposition the same place at the same time, or if you do that, you may have some additional characteristics. I hope my journey towards Yonsei University and coming back as a faculty at University of Madras has turned my research career and my research thought as well as. So, based on my experience in nanocluster, currently we are working on less known metal nanoclusters like Cobalt and so on. I will slowly build up why I have choose this topic and why this topic is very hotspot topic in the current scenario, and you'll be impressed about that. Okay. Going back to certain basic definitions, I hope for a good researcher you should have a current up-to-date literature survey, and you can see this article from Journal of Chemical Education about categorization of quantum dots, cluster, nanocluster, nanodots, etc., which is published in 2021, just this year, a few weeks before. Okay. So many of us work in nanotechnology, and many people coin their particle 300 nanometer, 600 nanometer, or somebody may coin plus 50 nanometer, etc. So nanoparticle and nano, the term becomes crazy among the research field. But you have to know the definition of what you are working and why you are writing that terminology, etc. Okay. So in that aspect, this particular paper, on this paper, you can see based on years and number of publications, they have made a chart, and you can see cluster finds its place right from 1960 and up to date. But what we are going to discuss is about nanocluster, which start late in 1990, and it is now hotspot chemistry, and there are several papers. But why I choose this article is that one has to have a clear definition what is a quantum dot. Okay, maybe a quantum dot is defined as a material showing quantum confinement effect in all dimension. That is what many people, quantum dots means you will be reflected to cadmium selenide quantum dots. You see, it is not only gallium selenide. We do have carbon quantum dots, we have gold quantum dots, and many. So quantum dots should be typically 2 to 15 nanometer. Basically, they are semiconductor in nature, and they are quantum confined, size dependent, and they exhibit photoluminescence property. What is quantum confined size? Because as the size is reducing, you can find many bands at the homo-lumo levels are able to be visible. Okay, that is what we call quantum confinement effects. I make it very simply. There are so much depth in it. Okay, and you know what is nanodots? Nanodots is nothing but similar to quantum dot, but they range from 2 to 20 nanometer. Mostly they are noble metal nanoparticles, and many people would have known nanoparticles should be in the range of 1 to 100 nanometer. But nowadays, based on literature experience, people have extended it to 500 nanometer. Okay, so what we are working at it is nanocluster, where every size, every atom in the particle matters. Okay, there is also a definition. Maybe since the audience can be from wide sector, if you are new to nanotechnology, see a particle size. If I say 2 nanometer, it doesn't mean 2 atoms are there. No, it can be 50 atom, it can be 70 atom, it can be n number of atom depending upon the atomic weight of that particular element which is present in that particle. So a particle is a collection of atoms which is stabilized by a capping agent or a stabilizing agent or by the one spot synthesis. Okay, so never define a particle saying 2 nanometer means it has 2 atoms. No, it is a collection of atoms which is having a dia of 2 nanometer. If it is having 2 nanometer, we call it as nanocluster. That is what we are going to see in detail. And what is this term means so big? Okay, so we have 2 different types of particle, which is called metallic particle. Another particle we call molecular particle. Okay, so far people are dealing with many papers. I feel only few groups are working on nanocluster in India, and you can refer it. I am not justifying that I am the top group, but I am telling based on my literature experience, very few groups are working on nanocluster, but many people are working in nanoparticle. But what is the difference between metallic particle and what is molecular particle? So metallic particle, what we are looking at is the SPR band, what is called surface plasma resonance, okay, which is by the conduction electron. Whereas cluster, it depends upon the core particle or the core atoms which is present in the particle will develop a molecular-like behavior. Means that if I say gold nanoparticle, once any chemist will say, or a material scientist will say, its wavelength 5520 nanometer. What is its size? No one can say. No one can say by the UV spectra. Rather, you can go for a HR10, and you can say even 5 to 15 nanometer will have the same wavelength, 520 nanometer. But here we say even a 0.1 difference of nanometer makes a difference in the spectra of the absorption pattern, and that is because of the molecular excitation at different sizes. Okay, so we are going to go into nanocluster, which is of less than 2 nanometer or equal to 2 nanometer size. That is the importance of this topic. Okay, from this slide you can take that message. Okay, right. So someone who is new to nanotechnology, what is the surface area to volume ratio? So what is this nanoparticle doing? One thing is the color. As the size differs, the color differ. Okay, that is what making this nanotechnology field very crazy. The other way is that how the surface area is increasing. Simply speaking, if you try to break a spherical particle into cubic particle or a cubic particle into different fractions, and that fractions into many multiple fractions, you can see The first cube had 6 faces. Then you broke down into 8 pieces, and on 8 into 6 faces, it will have another 48 faces. Then you break it into n number of times, and it will have many more faces. So the composite, which is made up of the brick, so the lady who is breaking the brick is making the particles smaller and smaller, means that every part of the brick is exposed to the composite, what we call cement, okay, to make a construction. Same way, every surface of a particle at a smaller size level is exposed to catalysis, is exposed to sensor, and so on. And each surface is able to contribute to the overall performance of that material. That is what surface area to volume ratio simply means. Okay. So I hope many would have known about what is the top-down approach, what is bottom-up approach. To make the particles small, we conventionally use this ball milling or grinding machines, where you reduce the size of the particle to a small size. Nanometers are not visible in naked eye. It should be made even more smaller. So this is one customly follow or conventionally follow physical approach of making the particle into a nano size. That is what we have been doing. But as a chemist, okay, there is another approach. So this is another slide which tells you about importance of small size. If you take as a mother who is feeding food to a kid, does not take the entire rice and feeds. She smashes and makes it into a paste level, and these paste have different smaller size of particles of rice, and they are able to be digestive to the kid at that age. And even if you take a cube of ice, okay, so these fine sizes will improve its efficacy either in the field where it is used. Okay, so that is only a colloquial way of understanding that what size means and what is small size means. And as you go down the size, I'm able to explore the surface area, and cumulatively I can improve the performance of that material. Okay. So what we are doing as a bottom-up approach is a chemical approach. We are starting from atoms. You can see at the right hand side, we are starting at atoms, and we are converting into cluster, and these clusters are converted into nanoparticle, and sometimes it goes to bulk level. But what chemists want you to do is, atomic level is 10 power minus 10. Okay, atomically precise, the atom atomically in the term which comes from 10 power minus 10 meters size. Okay, so we are closely going to atomic level. That is why I have mentioned atomically precise. Okay, if you take an example of gold particle, if you want to synthesize a gold nanoparticle or any nanoparticle, if you say gold is in 3+ state in a salt form, auric chloride. If you are trying to add a capping agent like thiol, what we have added here, we can add any capping agent, citrate, anywhere. It will initially reduced by the capping agent itself sometimes. Few may convert to Au+1, few may convert to, many are in +3 state. So if you use a reducing agent, very strong reducing agent, which is one of the constant required to prepare a particle, nanoparticle. So it starts to reduce to an gold atom. Atoms are very highly unstable, and they are in metastable state. What happens? These atoms will combine together to form a nucleus. Okay, that a metastable state means unstable means that they want a group of atoms to make it stabilize, and they form a nucleus, and this nucleus will build up into a particle. At this level, people are trying to restrict it, okay, to a fine size. What is the reducing agent you are using, and how you are stirring, and what type of capping agent you are taking will decide this particle size as a whole. Okay, for any type of nanomaterial synthesis, this is the practice what researchers are using. And here I have explained to you about gold nanoparticle. You can see different sizes versus different color. Okay, and these colors will have a different shift in the absorption band in the ultraviolet UV visible spectroscope. Okay. Okay, right. Okay, whatever I see is wine red color gold nanoparticle. Yes, I can see from the literature that if it is wine red color, I say it is gold nanoparticle. How do I confirm? We need to have a machine which tells that this is the actual size of your particle, what you have synthesized. So we use a technique like many techniques we have, and the most advanced technique is the high resolution transmission electron microscope, which is called HRTEM, which can go up to 0.5 nanometer to the best. Okay, we can also find core shell particle, rod-like shape particle, and so on. So the image shows the diffraction pattern of that particle. You can also have a correlation between this diffraction pattern and XRD study, okay? Because it will talk about the Miller indices which is present in the crystal, and it will be, you can confirm that with XRD also. Okay? So this is the actual image of this HR10. There are two types of TEM, bio-TEM and HR10. Biological sample, a separate TEM is also available. Okay? So now we have understood what is nanoparticle, how do I synthesize, how do I visualize, right? Okay, all I do this, but what is the use for the society? Okay, you do this synthesis, you buy this project, you do so many synthesis and publish so many papers, but is that of worth to society? Yes, it is worthful. Okay, see, at the university level, we are R&D faculty, where we are at studying about the material, and we are not here to sell products. Okay, so there are certain applications which are in literature and in the society where nanotechnology plays a vital role in cosmetics, military and defense. Nano supermarket is also there, and it is also finding wide application in automobile and healthcare. Okay, to go before into the core of nanocluster, I just want to literate you that nanotechnology is catching up. It is being catching up, and it is only these few slides are important for those who are new to nanotechnology. Okay, so you do have nano waves of invisible material where electrochromosome plays vital role in changing of color or showing the soldier invisible in the warfield, etc. And we do have arms which are the weapons or the cloth which they are wearing is of high strength. Okay, you can have an onion-like material. What is onion? Onion has several layers of. It is a vegetable which is having several layers. You can see the strength of this onion is because of this layer. There are certain materials which are like carbon nanotube or multi-wall carbon nanotube have different layers which gives high strength to the material. Okay, so certain arm materials which are made up of nanomaterials are lighter in weight, but they are very robust in nature. Okay, that is why people are going towards nanotechnology. So for a sake of students, we do have what is called nano supermarket, where you see we are in the place of in running. You know? Our generation is so if you start at 10 o'clock in the morning and 6 o'clock comes very at a short time, because that people are running, okay, towards their passion or towards their job, etc. And I think we are, some parts of the world are also shortage of meals and what you call the food. Okay, so we do have what you call magic meatballs. Magic meatballs is that we do have different forms of fruit which is filled with capsule or nano capsule, where if I take a piece of banana which I can withstand my hunger up to a day. Okay, there are technologies available where a fruit, even a small fruit, can give you an energy of a day. Okay, and we do have for youngsters like college students wearing different color shirt would have been a passion. Okay, nanotechnology is a solution where you can take a t-shirt and make a spray of your own variety of colors and you present your to your opponent. Okay, and counterpart. Okay, these are the simple form of nanotechnology which is being market. And we do have nano wine. I am not experienced to it, but it is literature reference that if you buy a product which is having a capsule, and with the help of microwave treatment, one can tune the level of intensity and the mood of this wine. Okay, so don't ask me where it is selling. I'm not here to say about that, but I am telling nanotechnology plays a vital role in all forms of field in our society. And another is nano jacket, where people use for marathon. We always depend upon the time watch towards when we run, but even our cloth color can decide the distance what we are traveling. So there are certain materials which are made up of nanomaterials which are in market. So it is not only at the lab scale, but it is also at the society level. And we do have cars. Nowadays, you can see cars of lightweight material, which are used thin layers of nanometer. Like here, you can see nano paints are being done with the organic binder, which give high resistance as compared to conventional paint. And in terms of corrosion, Also, one can use nanoscale silicon dioxide in order to prevent corrosions in the carbon in body of the automobile or the cars or the small weapons which they are using for automobile. Okay, so nanotechnology is having its place, its caliber in all types of field. Okay, and we do have what we call solar cars, which is having 120 nanometer of silicon balls, which can receive the heat from the sunlight and convert into energy. Okay, so nanotechnology has been there for the last 1 decade, and it has been extensively used in various fields. That is what I want to say. So now, as a basic new to nanotechnology, a person can understand what is nanoparticle, how do I visualize, how do I synthesize, and what are the fields which are there which nanoparticle can be invaded and is being in use. Now I will come to my topic of interest, what is nanocluster. Okay, this may be advanced topic for a PG level or a scholarly level, where you can have these 3 papers which are published in Nature, JACS, and I am one of the author in JACS 2015 from the Yonsei University. I will tell you what is the contribution I have made in this paper. First of all, you can see silver 44. Okay, silver 44 is about 1.4 nanometer. You see, so far in literature, people have been telling gold is an inert material. Gold is highest stable material. The first stable metal nanoparticle one could say in literature is gold. But to your surprise, you see that in Nature 2013, silver 44 has established high superior stability as compared to gold. Okay, that is why it has been revolutionary and it is published in Nature. Okay, and we do have what is called gold 25, 180, and these are the number of ligands. Nowadays, we can work on the nanoparticle. You can see this particle size is only 1.1 nanometer. So 1.1 nanometer has 25 atoms of gold and 18 ligands. Okay, so nowhere you can define, if I say 1 nanometer, only 1 atom. No, if it is for gold, it is 25 atoms are present on that one particle. That is what collection of atoms forms a particle. Okay. So, and we have what is called gold 22, and gold 22 has established the highest photoluminescence of about a quantum yield of 60%, and that is why this paper has been very cited in JACS. And gold 22 has a redox active property. I will tell you why gold redox property is very interesting. Okay. So these are my main topic which I want to share with you. See, okay, how do we synthesize this nanocluster? Right. Okay, I take a gold salt in an aqueous medium, and you can phase transfer this with the help of PTC in toluene medium. That means organic medium, and you can add thiol to it, and it will. I said the steps which already it forms an atom, and atom will form to a particle. You can see the different stages happening to the particle. See, initially it is slight yellow in color, then it turns to orange color, then it turns to white precipitate like, and then it converts to a brown black precipitate or a solution which is having a cluster. Okay, these are the mechanisms involved. Concerning this time, I'm not to go into the details. You can find this article in Langmuir 2013, okay, about the mechanism of metal nanoparticle. Right. Okay. Okay. So I said size matters, right? So many people do synthesis of nanomaterial, but many people are not focused about the size. If I get 5 nanometer to 50 nanometer, beautiful. The images are so neat, but you see now the literature is going towards atom by atom. So one can substitute an atom of gold and put a palladium into the lattice, or you can substitute a platinum into the lattice. Accordingly, the property also varies. So we are in that state, but we have to transform from polydispersed particle to a highly monodispersed particle. So such interesting properties are only achieved in monodispersed particle. And one way of separating or isolating this particle in a uniform size is that solvent fractionation. What is solvent fractionation? You can take 2 typical solvents like water, methanol. Okay, you try to wash this crude particle after your reduction, and you try to see that you get a superabundant liquid and a centrifugate. I mean, at the bottom you get a precipitate and a solution. You separate this solution. Again, you wash with another ratio. Maybe example, if I take a 10 ml of solution, water, now you take next, you take it as 9:1. Then you take 8:2. Then 7:3. You try to wash these different mixture of solvent with the crude particle. You will get different size of particle, and each size will correspond to different number of gold atoms or silver atom, whatever you have prepared. Okay, because the number of ligands around this particle will decide the solubility of the particle. Okay, so if it is small size, the ligand number is lower. If it is going to be larger size, larger the ligand, the size will go to a smaller size. But what I mean is that the solubility is induced because of this, what type of capping agent you are using. Okay, so the ligands will decide what solvent I can use to do a fractionalization and separate different size particles. You can see at the right extreme, I have gold 144 and gold 25. These are two different sizes. You see to the beauty, gold 25 is 1.1 nanometer and 144 is close to 1.6 nanometer. We are only playing with 0.5. Okay, and it is highly monodispersed. Okay, if you use acetone in this mixture, gold 25 will be soluble in acetone. Rather, the larger side cluster will not be soluble in acetone. Okay, solvent plays a vital role in separating monodispersed particle from polydispersed crude particle. Another way is very simple way. What we have been using is a filtration. Okay, we are having nowadays different types of filter paper of different Daltons. Okay, so you can buy a filter paper of 10,000 Dalton, 5,000 Dalton, and use like a syringe type of separation where you pour your crude particle and you separate. Depending upon the membrane size, you are able to isolate different size of particle, and their patterns also differs. You can see the absorption patterns for this one is completely different from this particle. Okay, so this is filtration technique. Okay, so I said what is my contribution in Jackson 2015 paper is that PAGE. Okay, PAGE is not new to biologists or people who are working in biology relevant chemistry. Is that PAGE is defined as polyacryl gel electrophoresis. This technique is based on separation of molecules based on its mass to charge ratio. So depending upon the mass and the charge, it is able to selectively separate particles when you apply the potential. Okay, so, the migration of particles will take place from the top to the bottom. Depending upon the size, they will isolate like this. What I have shown in this image at the right side. Okay. So here I tried to establish this procedure at Yonsei University, and see from the slide you cannot convert anything. That is why I am confidently presenting that. Say this confident also many will not have that people who take our literature idea. But I welcome you. You take it, but you don't think that by the slide you can convert everything to another question. You need experience. You need time to do it. Okay, so the gel which we are making is based on acrylamide, which is the monomer, and we use a cross-linker methylene bisacrylamide, and we have two important things, timide and APS, ammonium persulfate, which initiates this polymer. Okay, depending upon the percentage of this polymer gel what you are making, the size will vary. You can see here for 10% it is 10,000 Dalton to 68,000 Dalton, whereas if it is for 22.5%, it is 8,000 to 30,000 Dalton. So as the percentage is higher, the pore size of this gel will be smaller. So pore size will decide what type of particle you can separate. Okay, so if you tune this percentage of gel making with the constituents which is available here, you can separate clusters. But here the problem is yield. So you will not get higher yield with this technique, but you will not miss out a small cluster from this crude sample. But in solvent fractionation, you will miss out the very small new cluster, but there you will get higher yield. Whereas here it is a greener technique, the yield is low, but certain new compounds, new particles can be isolated by this technique of PAGE. Okay. So this is the setup which is available. It's a mini tetracell PAGE component, which is now around 2.5 to 3 lakhs unit, which is available in Biored company. And nowadays we have commercial also. but this will be the best. You can see what we do is that these are the two plates, glass plates, which are available. Is able to, you have to reposition it in this clamp, okay, frame, and you have to position this in the stand, casting stand, and you have to pour your solution before polymerization. Okay, I'll tell you the steps here. So you can see we have to place a comb, what you call a fiber, plastic like comb, before you pour the solution. What solution? I have given you a table. So these are the resolving gel. You have to make this to, if you assume 10 ml, these are the constituents like water, acrylamide monomer, HCl, glycine, APS, timid. So you prepare a solution immediately, because if you add APS, polymerization will start very fast. If you miss timid, acceleration will go. Okay, so the polymerization has to occur very fastly, as well as you have to pour the solution inside the space available in the slides. Okay, then you place the comb, and after some time you try to remove this comb. You can see the wells available. These are the wells where you have to pour the sample, and you connect it with a capacity, and you try to apply a voltage and a time that will separate like an individual cluster. Each band corresponds to each size. So you can see here the bands which are available. So the lowest band we have achieved is 1.1 nanometer. Okay, that is gold 25. Okay. So this is the technique which I have been experienced. Page is not new thing. Page is not the one thing Prabhu has shown. Prabhu has shown phage technique to nanomaterials lab at Yonsei University to separate cluster. Okay. So I took a time of 3 months to achieve this. Okay. Because I am a chemist, if I have been experienced in biochemistry, this page would have been very familiar to me. But after my PhD, only I was exposed to this page technique. Right. Okay. So what is the use of this cluster separation? Dr. Prabhu, if you ask me, see, each size will have different property and unique property. See, I think many people would have worked in gold nanoparticle and would have taken electrochemical response. You can see gold particle even at a size of 1.23 nanometer, okay, 1.2 or 2 nanometer will not establish any redox behavior. What is redox behavior? If the delta IP is going to be equal to or less than 60 millivolt, okay. So see, to the beauty of this gold 25, it is able to show, gold as such 1.2, 1.3 will establish a quasi-reversible response. Okay, you will not get a redox peak. Here, for gold 25, for the first time, we were able to achieve 2 redox peak. Okay, for gold. Okay, that is why it has been revolutionary, because to use mediator in sensor like chemical sensor or biosensor is a prominent entity. So people try like dyes, they use ferrocyanide, so many things. So these are highly not inert, okay, they are toxic also, but gold is inert and non-toxic. Okay, if gold is able to give a redox property, it can itself act as a mediator and electron conductor. This is one of the beautiful material which we have to develop various types of sensor, but I say you, it is not easy to prepare. Okay. By experience, you have to develop. Okay, correct. So this is what I was trying to say. The electrochemical response of gold is quasi-reversible for a particle up to 1.2 nanometer. But if your particle is exactly 1.1 nanometer, 90 to 95%, 8,000 kilodalton size in the China, it will develop a homo-lumo gap and it will develop a redox property like this. I'll tell you the application of this. That is what it is, the transition of metallic particle to a molecular particle. Okay, I'll tell you that here you can see the relative potential difference between the number of atoms present. You can see this is a bulk. What you mean by bulk? Even 1.5 is a bulk for gold 25. Okay, even 2 nanometer is a bulk. So that is, you start from here. You can see gold 22, 225, 140, 75. They have quantified it with the help of multi. Okay, and 38. Now 25. You can see the homo-lumo gap. What is homo-lumo gap? This will decide the electronic transition both in photochemistry as well as in electrochemistry, where the gap is around 1.3 electron volt. So as the number of atoms is decreasing, this homo-lumo gap is widening up, and this homo-lumo gap will decide the electrochemical behavior of gold. And you can see different types of ligand have different homologo variation, and it is reported in this paper. Okay, what is the use of this? Okay, I have developed a material with a redox activity that is gold 25. But you can take this gold 25, you can see the 10 image of 1.1 nanometer, mostly close to 1.1 nanometer, and you can see the response of this UV. I said you gold nanoparticle will give you a peak at 520 nanometer. That is, I hope most of you would have seen metallic particle, but this paper talks to you about molecular gold particle of gold 25 with a 1.1 nanometer. You can see the UV pattern is completely different. Okay, there quantum confinement plays vital role, and different excitations takes place. For time constraint, I don't want to see certain place. If you go into depth, what you have understood earlier will miss out. So I don't want to go into this depth. It has very complexity, that it has different excitation and transition states which are expressing in this gold 25 at 1.1. So you can confirm this size and the number of atoms with the help of MALDI, and you can see the electrochemical response. And actually we have, not we, the group from our Professor Dongli have used ionic liquid with gold 25, and they have coated on the electrode. Okay, what is ionic liquid? It's a highly viscous liquid, because anything you coat on an electrode, it has to withstand. It should be, it should not foul away. Foul away means it should not strip from the electrode when it is inverted into the solution or an electrolyte. Okay, so we need an ionic liquid matrix to make this particle to stick onto the electrode, and thereby you are getting this response. You can see the first oxidation peak is because of the -1 to 0 state and 0 to +1 state with the second oxidation, and you can see beautiful redox behavior from gold. This is an historical paper on developing sensor based on gold redox activity. Okay. So based on scan rate, this response is also differing. You can see a paper on the ACS Nano where they used enzymes with this gold 25 and able to sensor glucose. Okay, you can see the glucose can be sensed, and the calibration plots shows about how much you can tune both the enzyme as well as gold 25 concentration in that matrix, and you are able to develop different calibration plots. But what I want to say is that gold 25 acts like an electron hopping process. Okay, it is also acting as a mediator as well as it is acting as a redox electron conductor. Okay, so from enzymes, glucose are converted to gluconate, and this electron is received by gold 25. It is transferred to the electrode, and this is signaling as this response. Okay. There is so much complexity in this slide due to time constraint. Okay, there is another material which I said ultra stable gold silver 44. Okay, you can see here this is a group from Terry Bigioni from US. They have published this. I said you page can give you plenty of bands like this variety of colors in a single crude sample. So the nanomaterials which we are synthesizing can isolate several particles of this color. You can see each color will corresponds to a particular size. Okay, so this is a page sample, and from page you cut this gels, and gel can be dissolved in water to convert into a particle. You can dry it and convert it into powder also. Okay, so see the beauty of this absorption pattern. Different bands produce different absorption pattern. Means that they are different size. Okay, you can see band 2 shows this type of pattern for silver, and band 13 from this page image shows this type of absorption pattern. So there is a complete quantum confinement effect where size matters, and you can see over a period of time the absorption stability. Okay, as you increase the time, the band stability can be arrived from this. The band 2 seems to be highly stable as compared to band 30. Okay, so clusters, many people are very worried to work is that its stability. So you can achieve stability by the help of using an appropriate capping agent and stabilizing. And now that this paper is published, I said you this paper is published in Nature in 2013, and this is the UV visible pattern of that silver 44, and you can see this plot. Gold 25. Gold is so far considered to be highly inert, highly stable, but you can see this paper. gold 25 is the yellow dots which is shown here, which is having a drop in stability concentration, whereas you can see silver 44 is able to have a better stability as compared to gold 25. So that's why this paper has been published in Nature. It is carrying lots of. What is this size matters and it is giving unique property? It is because of its structured nature. Okay, they possess some unique structure. Depending upon the size, they will have a core and there will be a shell, what we call staple modifier. Okay, and they will correspond to particular shape also. Okay? Usually it is decodacral or isoacral, etc. Okay, so the third thing I want to suggest you is that gold 22. Okay, so in this paper only my contribution directly impacted by the page. Okay, so you can see my authorship here. I have missed out the position because I have been appointed as a professor here. After that only this publication came. But anyhow, they have recognized my work. Okay, you can see that the robust stability. The beauty of this paper is so far before this paper, gold 25, gold 22 had 8% of quantum yield. But this paper reported the highest quantum yield of 60%. Even a 0.5% increase in quantum yield in photochemistry papers is extraordinary. But you can see here from 8 to 60%. Okay, so these are the gel separation done by the postgraduate student based on my experience. And you can see the response of this gold 22 is like this. Here, what they have used in phase transfer catalyst, because you know in photochemistry and photoluminescence, a robust nature will increase the quantum yield. So we used TOA, tetraoctyl ammonium ion cation, to shift gold 22 from aqueous to organic medium. So thereby this quantum yield was even more increased, okay, to 60%. So this is the conventional rhodomine dye quantum yield. Most of them use this rhodomine dye for the standard. Okay, it is performing more than the standard. Okay. And these are the relaxation patterns based on temperature. The photoluminescence behavior is differing, and you can see here the different confinement effect. Quantum confinement is that as you go down the size, this conduction band, valence band, internal bands will explode. Okay, they start to widen up. Okay, and they also give a higher lifetime of greater, 200 femtoseconds. And these are the reasons for this high quantum yield. And okay, so these are my postdoctoral experience so far, which I have been doing. Now I should do something at Madras University, right? So I cannot blabber something that. So we were shifting this gold work towards cobalt, because cobalt smaller size is papers are very limited and cluster reports are not there. And we took glutathione as a thiolate and we converted gold cobalt cluster, and we got different bands of different color, means different size. And you can see these different size had different quantum yield also. Okay. So this paper was published in Chemistry Select after a severe review. So these are the absorption patterns. So the bands had different absorption pattern, and you can see the size also varies. Okay. So different bands had different sizes. So our aim should be towards highly mono dispersed particle. You can see this, a crude particle had no photoluminescence for cobalt cluster, but a page separated cluster gave a photoluminescence. That is the success of this paper. It has been published with a blue emission. Okay, and it had different lifetime, it's a transition timing also, lifetime. And another paper we have published in Journal of Physical Chemistry C last year, along with Professor Muthuraman from Energy Department, is light harvesting material from cobalt nanocluster. Okay, you can see here, we try to use cobalt in aggregate form. There are two terms in nanotechnology: aggregation and agglomeration. Okay, agglomeration is that smaller particles combine to form bulk particle. They lose their property, nanotechnology affected. But aggregation is that small particle combine together to form a cluster of small particles, cluster of individual particles, not bulk particle. Okay, agglomeration is converting a nanoparticle into a bulk particle, whereas aggregation, a small particle will group together, form like an assembly. Okay, based on the metal to ligand ratio, the electrochemical response of this cobalt were differing. Okay, and that's why this paper was published. We tried to give. So you can see it was forming like an assembly. That is what we want to say, an aggregate with an assembly. So another paper we worked on copper nanocluster, which was published in ACS Applied Material Interface with an impact factor of 9 last year with Anandan Ramaswamy from Organic Chemistry, where here it is also interesting where cobalt 1 state in the cluster is able to convert what you call acide to diazide. Okay, you can form diazide here, whereas usually if you have two acide group in a molecule, so far in the copper catalyst were able to convert simultaneously both the terminals into a cyclic compound. But particularly this catalyst are able to selectively cyclize one acide. In the second click, it was able to cyclize the other part. So the beauty of this paper is that it had a selective cyclization property, and that's why it was able to accept in easy applied material science. And we were able to confirm that these particles are cubical in nature, and though they are cubical, they are still in the range of 4 nanometer. And these are the organic part of it. So we had two acide, it converts into one cyclization. But if you use a copper with what we call metal organic framework, okay? So far report shows you have to mask one end and then cyclize. Then only you can do selective cyclization. But this catalyst directly had a selective catalyst, selective cyclization, and in the second click you are able to do the second cycle. Okay. That is the beauty of this paper which was published in ACS. So without students, nothing can be done. Without manpower, we can't do anything. Though we have ideas, these are my scholars who been there with me since 2016 in elevating me in this publications or research exposure. And these are my achievements and a few awards which I have won, and hoping to do better. And I have shared with you confidently that current topic which we are doing at the University of Madras, and I'm encouraging you to continue that work. But if you don't think at one spot you'll get this, you need experience. And if there is any question, I can take it. Thank you for your patience. And this is my postdoc group. Thank you.
Thank you very much, sir, for your valuable talk. And you have done a great job in nanocluster research. And I have a question, sir. Can you hear me?
Yeah, now.
Sir, in chemical synthesis, we have yield issues. So how to work at yield issues in chemical synthesis, sir?
Yield issue is that, with regard to nanomaterials, which I am sharing, is that it is about playing with the metal and the ligand, the choice of the ligand, what you are working at. And since we are, if you take a page, that's what I said, page will give you low yield, but it will not miss out a small cluster. Small cluster means 1 nanometer or 1.1 nanometer, etc. Even 0.1 nanometer makes a difference in the structure, property, and so on. So to have a very small cluster, we have to, or a newer cluster, we have to go to page. If you want yield, we can take solvent fractionalization, where we use different solvents, and you can have much yield there. Okay? So one technique can be a quantitative, the other technique can be qualitative. You can apply it.
Okay. Thank you very much for your answer, sir. And as a token of appreciation, we would like to give you an appreciation letter from our organization, sir. Please be kind enough to accept it, sir.
Yes, thank you. Thank you. If there is any question from the audience, I am ready to answer.
I don't think so, sir.
Okay. Okay, hope they didn't sleep. Thank you.
Thank you very much, sir. Thank you. And now I call upon our my colleague, Dr. D. Kavita, Associate Professor in the Department of Chemistry, to propose vote of thanks.
Good afternoon, everyone. This is Dr. D. Kavita, Associate Professor, Department of Chemistry. Taken this opportunity to propose a vote of thanks on behalf of the organizing team. I thank all the dignitaries from our founder, Chancellor Dr. A.C. Sanmugam sir, President Engineer ACS Arun Kumar sir, Vice President, Vice Chancellor, Pro Vice Chancellor, Provost, all register, our Dean Dr. S. Manivannan sir, and our Head of the Department Dr. L. S. Valliyamai Madam for her continuous encouragement and support. It is a great pleasure in thanking our Deputy Dean Dr. Arunachalam sir, who given his validity note. On behalf of my university, my special and heartful thanks to our today's speaker, Dr. Prabhu Pandurangan, Department of Physical Chemistry, School of Chemical Science, University of Madras, who delivered his presentation in a well explained, useful, and interesting manner. Thank you, sir. I extend my sincere thanks to all the participants for spending your valuable time and listening us. I would like also thank all the panel members, Dr. L. Ramapriya ma'am, R. Nitya, Mrs. Sasikala, and Mrs. Jeevarathinam, Assistant Professor from Department of Chemistry, and Mr. Ganesh Babu sir, Technical Assistant. I would like to thank once again all the participants for making this event a success manner. Thank you all. Thank you.
Thank you all for your cooperation and stay with us for our next program.
Dr.M.G.R Educational and Research Institute, University, Mother of All, Chennai.